Alright, so far, in this part of the unit, we've defined speed, we've talked about the difference between speed and velocity. Now we have to talk about another difference, that between average speed and velocity, and instantaneous speed or velocity. So first thing I want you to do is picture a car speedometer. That tells you, that's right on the dash. What does it actually tell you? Is it telling you the average speed of the car? Because that's the only speed we've talked about so far. Is it telling you the average speed over some period of time? It's really not. What it's telling you is your speed at one instant right now. It's telling you how fast you are right now. Because otherwise it wouldn't be very useful. If it told you your average speed over some period of time, wouldn't the speedometer be near zero most of the time because most of the time you're not driving that car? Absolutely. In order to obey a speed limit, you need to know how fast you're going right now. Okay? So, a car speedometer shows you something fundamentally different than the slope of a best fit line. They're both useful in different ways because they tell you different things about motion. The former, the car speedometer, is a measure of what we call instantaneous speed. And I'm just going to go with speed with these notes because it's easier to say than velocity. But this all applies to velocity as well. A car speedometer tells you the instantaneous speed of something, while the second, slope of a best fit line, measures the average speed of an object. Okay? I'm going to talk about average speed first because that's what you're most familiar with. The definition of average speed is the mean rate of change of distance over a period of time. Okay? This is literally, it's right in the name. It's the average speed an object has over a period of time. Now, how do you find it? How do you determine the average speed? Well, there's two ways that you know of. You take the slope of the best fit line over a section of data points. That's one way to find the average speed. That's what you did on your lab. That's what we've done when we've seen pictures of graphs. Or what you can do is you can use this equation. V hat equals D over T. There you go. That's the other way to find the average speed because that's what V hat means. V hat, that hat, the line over the V or over any variable always means average. However, if you're given a graph, the first option is better. If you're given a graph and you're asked to find the average speed, just use the slope of the best fit line. Okay, that's the better thing to do. If you don't have a graph, feel free to use that equation. Or make a graph of your own. Doesn't matter. Examples where this is useful, just kind of very general situations. This is useful when you are calculating distances and times for any large motion, for any extended period of motion, such as your, another example would be finding your speed over the course of some sort of race, something like that. That's when you wouldn't want to know your average speed, some large extended motion. Instantaneous speed, on the other hand, is the speed an object has at a single moment in time. Okay? The speed of an object right now. Now, the weird thing about instantaneous speed is it's actually pretty much impossible to find the speed right at exactly at one instant. Instead, what we do is we actually find an average speed, but over a very, 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 very small period of time. If you're in pre-calculus right now, then towards the end of the year, what you're probably going to learn a little bit about are limits. And what a limit is you figure out, it's basically what happens to an equation if you impose some limiting factor on it. So essentially, we're trying to figure out what the average speed would be if we take the time period over which we're finding the average speed and make it very, 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 very small. So, how to find instantaneous speed? It is known as the midpoint method. That's what I call it. I don't know if that's like the official name for it. I call it the midpoint method. Midpoint method means to find the speed at some point in time. Then what we do is we find the slope between the two adjacent points. Okay, so for an example, let's say you want to find the speed at point, let's say number 2 on your graph, the second data point. What that means is you would find the slope, or the change in y over change in x between the two data points to either side, so that would be points 1 and 3. And since we're talking specifically about distance versus time graphs and instantaneous speed, that would look like this. To find the speed, the instantaneous speed at v2, we would find the difference in distance between d3 and d1, the third point minus the first point. Divide that by the time difference between the third point and the first point. So notice what we're doing here, and I'll get to this when we talk about, when we see the graphs down here. What we're essentially doing is we're going to the data points around the point where we're trying to find the speed. Okay, and I'll illustrate that again when we get down here. Where is this useful? Why do we care about average or instantaneous speed? This is useful, and I apologize for the cramped writing, when you're talking about a car's speedometer, when you're talking about any sort of max speed listing, so what's the fastest something can go. Radar guns, either those used by police or those used by people to figure out how fast a baseball is being pitched or something's being kicked or thrown or hit. Radar guns calculate instantaneous speed. Basically, anytime you're looking for the speed at one instant in time. Doesn't even have to be a particularly fast speed, just the speed right now or at some point in the future. Okay, so that's the difference between average speed and instantaneous speed, and you need to understand that those two things are not the same. Okay, they're definitely not the same. They can be related and they can be equal to each other, but by definition they are not. They're not the same thing. So now what we're going to do is we're going to look at how to measure average and instantaneous speed on a graph. So I've given you a distance versus time graph right here, and the one thing that you'll notice about the distance versus time graph is it's extremely linear. As a matter of fact, the data is perfectly lined up. Okay, it's literally on a line. So our directions here say to draw a best fit line for this graph and write the equation for this line. So I will do that. I'm going to set my protractor up. I'm going to draw my line of best fit. Okay, there's my line of best fit. Now I get to write the equation for this line. Well, in order to do that, I see that the y-intercept is 0, so I don't have to worry about that, but I do need to figure out the slope. Nicely for us, all the data points fall along this line. Now, that's never going to happen in real life. In real life, you know that the data points aren't all going to fall along that line. I'd be very suspicious if they did. Okay? But the nice thing about this is this means I can use any data points I want. So I'm going to use, just for the heck of it, I'm going to use this data point that's on the line and this data point that's on the line to figure out what the, let's see here. Actually, no, I'm not going to use those. Those are kind of hard to read. I'm sorry, I apologize for that. I'm going to use this data point and this data point. The reason I'm switching is because those data points, it's a little bit difficult to read exactly what the what their y coordinate is. So if we're looking for the slope, remember that slope is y2 minus y1 over x2 minus x1. You have to remember that for calculating slopes. y2 is up here. It's this point right here. y2 would be 6 meters minus, let's see, that looks like 3 meters. x2 is, let's see, 10 seconds minus 5 seconds. 6 minus 3 is 3. 10 minus 5 is 5. 3 over 5 is 0.6 meters. So that's the slope. Therefore, the equation of my best fit line is y equals 0.6x. I could change the y and the x to d and t respectively, but I'm not going to in this case. So we know that the slope is 0.6 meters per second. And what does it represent? Okay, remember it's a distance versus time graph. Therefore, the slope of a distance versus time graph represents the speed of whatever object we're modeling, whatever object we're graphing the data for. So this is the speed. And specifically, because it's the slope of a best fit line, is the average speed over the interval from 0 to 10. On average, over this interval, the object was moving at 0.6 meters per second. Now, what I could do is I am asked to find the instantaneous speed at 2 different points. And we're going to talk about how to do that. I'm going to choose that we're going to find the instantaneous speed at t equals 2 seconds. That's the first one. Okay? If I want to find the instantaneous speed at 2 seconds, then I write down my midpoint formula. The midpoint formula is the velocity at 2 seconds equals d3, the distance at 3 seconds, minus the distance at 1 second, over the time at 3 seconds minus the time at 1 second. The bottom part's pretty easy to figure out. That's just 3 seconds minus 1 second. The top part, the distance at 3 is a little tiny bit below 2. It's actually 1.8 meters. And the distance at 1 is just a little tiny bit above halfway between 0 and 1. That's 0.6 meters. Okay, and those are the actual numbers. I made it this way specifically for this purpose. All right. So if I do the math, 1.8 minus 0.6 is 1.2 divided by 2, and I get an instantaneous speed of 0.6 meters per second. That's v2. Let's try another instantaneous speed. Let's take the instantaneous speed at t equals 7 seconds. For this one, I would be writing down v7 and try and guess what the subscripts on the distances and times should be. v7, I need the data point before and after that, so I need the 2 data points adjacent to that. That would be at 6 seconds and 8 seconds. So what I'm going to write down is d8 minus d6. Okay? The numbers aren't the important part. The important part is that you realize that for the midpoint method, what we're doing is we're finding the velocity at this point by taking the slope of the line that connects the 2 data points on either side of it. So in this case, that would be the data point at 8 seconds and the data point at 6 seconds. That's what we're doing here. It's a kind of a roundabout way, but essentially what we're doing is we're saying, the best way to figure out the speed at this point is by looking at the data points around it. Okay? I don't just want to do 7's distance divided by 7's time. That, trust me, it will work out in like 20% of cases. The other 80% is going to put you way off course. Okay, not good. So what I want to do instead is I really want to use the midpoint method. T8 minus T6. Okay, and we'll talk more about the midpoint method, and you'll practice the midpoint method in class. The distance at 8 seconds looks to be about 4.8 meters minus let's see, 6. Not quite, a little bit above halfway between 3 and 4. So that is 3.6 meters. And 8 seconds minus 6 seconds. And you probably are noticing something a little strange with my instantaneous speeds here. And you're like, why are you even bothering us to show us this? Because both of them so far have come out to be 0.6 meters per second. The exact same as the average speed. And that's not always going to happen, but this is a very special case. Okay? This is a very special case because all the data points were exactly in a line. All right? The speed, the average speed was between all the points was exactly unchanging. So this is a special case because for a constant, and constant just means unchanging. Okay, you have to remember that constant is the opposite of changing. If something is constant, it is not changing. For constant speed, something's moving at a constant speed, like this is, and we know that this is because all the data points are exactly the same y distance away from each other. For something moving at a constant speed, the average speed is equal to the instantaneous speed. That is not always the case. For something that is accelerating, for instance, for something whose speed is changing, you'll see little variations in the slope, and that'll show you that the average speed over some interval is not necessarily equal to the instantaneous speed. Okay, but if you see a perfectly linear slope, okay, like data points that are right on the line, you can infer that the average speed must be equal to the instantaneous speed. All right, I think I'm going to do one. No, I'm going to cut it off there. Okay, we're going to do the back when I come back for the next video.